Okay, so let's look one more time at the area underneath the curve, x squared, f of x equals x squared from 1 to 3. And we found last time that we could do a pretty close approximation of this integral using this formula. 26 thirds plus 8 over n plus 4 over 3n squared. So we got a pretty good approximation here. Now we talked in an earlier video how approximating this area using rectangles has some flaws, right? Because if I used one rectangle, I've got all this space here that's extra. If I used two rectangles, so I'm using my right-hand rule, I'm doing it a little bit better, but I've still got too much space. I've got less extra space, but I've still got too much. If I did two rectangles, I'm sorry, not two, but four rectangles, we're getting a little bit better, but still not great. 8 rectangles would get even better, but still not great. So really the message here is the more rectangles we do, the better we're going to get, right? The more rectangles that we do, the better we're going to get. So what we would like to do is we would like to take our definite integral and calculate our Riemann sum, which looks like this. But we would like to make the number of rectangles, remember n is the number of rectangles, we would like to take that out to infinity. So we're going to take our limit of our Riemann sum, and we're going to push the number of rectangles all the way out to infinity. We want to get an infinite number of rectangles here. And if you think about that too, we're making our rectangles infinitely thick. We're making this number on infinitely thin. We want the denominator of this fraction to get infinitely small, which basically means we're just doing like lines, right? We're just doing little lines, an infinite number of little lines to get this whole entire area covered up, and that will give us equality here. So we're going to calculate this definite integral by calculating the limit of our Riemann sum, our general Riemann sum with n rectangles. And then you'll notice, right, that this width, this delta x, ends up going down to 0, which we don't really want to multiply this by 0, right, because that's going to make it go away. So where our delta x is turning into an infinitesimally small little distance, and we're using our dx to be that differential distance, that little infinitesimally small little distance there. So that's where the dx is coming from, is it's really the delta x, but just infinitely small. And these are still being multiplied. Okay, these are still being multiplied together, just like they were being multiplied over here. So don't think of this dx as being like a part of the integral. It's really, we're finding an area here. We're finding the height with our f of x times this infinitesimally small width. So that's pretty handy. So once we have our Riemann sum here, this is like this. We're going to say this is equal to the limit as n goes to infinity of this sum. And then recalling some things about limits, right? Just like this fraction kind of goes down to 0 as the n goes to infinity. These fractions do too. This fraction goes to 0. This fraction goes to 0, and we're just left with this number. And so this integral, that area, is exactly 26 thirds units. So that's pretty powerful. Now, a page long of work went into finding this Riemann sum, so that's kind of a pain. There's got to be a better way, and there is. So in a later video, we'll see, what's an even better way of finding this answer to solve this integral.